In this video, we restrict the domains of the sine and cosine functions so that the graphs satisfy the horizontal line tests and therefore become graphs of invertible functions. And use reflection in the line y equals x to visualise the inverse sine function. We also sketch the graph of the tan function and repeat this process to describe the inverse tan function. Here are the graphs of the two circular functions, y equals sine x and y equals cos x, both producing sinusoidal curves and wave patterns that replicate infinitely often as one moves back and forth along the real number line. Both sine x and cos x are defined for all real numbers x, interpreted as angles that wind around the unit circle. The domain in both cases is R, the whole real line. Because we move from points on the unit circle across to the vertical axis of sine x and down or up to the horizontal axis of cos x, the values are trapped between plus and minus 1, so that the range is the interval from -1 to 1, including both endpoints. Graphs of all functions automatically satisfy the vertical line test. What about the horizontal line test in these cases? In fact, any horizontal line that touches either graph passes through infinitely many points. So the horizontal line test fails spectacularly for both graphs. Remember, for a function to be invertible, we need the graph to pass the horizontal line test. So neither of these look like they have any hope of being invertible. Well, there is hope. We can severely restrict their domains so that we get a fragment of each graph that passes the horizontal line test. For the sine curve, we box in this tiny part of the curve, ignoring everything else. It's standard to restrict the domain to the interval from -π/2 to π/2, including both endpoints, and then we get this fragment of the original sine curve. Note that the range remains the same, the interval from -1 to 1. This fragment has a very pleasant rotational symmetry about the origin. The curve coincides with itself if we rotate it 180 degrees, an instance of being an odd function, a concept that's important in future videos. For the cosine curve, it's not so clear what to choose, but everyone agrees to box in this part of the curve, restricting the domain to the interval from 0 to π, producing this fragment, and again the range is unchanged, the interval from -1 to 1. Here are the two fragments, and you can see that horizontal lines pass through these curves at most once. They've been deliberately chosen to both pass the horizontal line test. Let's see what happens to this fragment of the sine curve when we reflect in the line y equals x. To simulate the reflection, we can take a transparency with this fragment and flip it over. Here are the fragment, the line y equals x, and the reflected image all on the same diagram. And here's the reflected image on its own. The roles of input and output have been interchanged, so the labels plus and minus π/2 now become points on the vertical axis, and the labels plus and minus 1 now become points on the horizontal axis. And we have the graph of y equals inverse sine of x. Remember, inversion interchanges domain and range, so the domain of inverse sine is the range of sine, which is the interval from -1 to 1, and the range of inverse sine is the domain of our fragment of the sine function, which is the interval from -π/2 to π/2. Just think of the sine function as taking angles to numbers, and the inverse sine function as bringing numbers back to angles. Now, of course, angles are numbers if measured in radians, but it can help to have some kind of mental image of a geometric angle that is the output of inverse sine. For example, sine of 30 degrees, or sine of π/6 radians, is a half. So inverse sine of a half gets you back to 30 degrees or π/6 radians. Maybe you conjure up in your mind an image of a 30-degree right-angled triangle with opposite side length 1/2. Sine of 60 degrees, or π/3 radians, is √3/2, so inverse sine of √3/2 gets you back to 60 degrees, or π/3 radians. Sine of 90 degrees, or π/2 radians, is 1. So inverse sine of 1 gets you back to 90 degrees, or π/2 radians. Sine of minus π/2 is -1, so inverse sine of -1 gets you back to -π/2. Here's an application. Suppose a kite is flying 40 metres directly above the ground, but fastened to the ground by a piece of string which is 50 metres long. Assuming the string is approximately straight, we want to estimate the angle of elevation, which we call theta. In the diagram, you can see a right-angled triangle with angle theta, opposite side length 40 metres, and hypotenuse represented by the string of length 50 metres. The adjacent side is the ground, but we don't need to know what its length is to solve the problem. To solve this, observe that sine theta is the opposite over the hypotenuse, which is 40 over 50, equal to 0.8. To get back to the angle theta, we take the inverse sine of 0.8. If your calculator is in radian mode, then you should get 0.93 radians to 2 decimal places. If it's in degree mode, you should see 53 degrees to the nearest degree. This checks out because 53 multiplied by the conversion factor pi on 180 is approximately 0.93 radians. The analysis for inverting the fragment of the cosine curve is similar and explained in the notes. I'd like to spend the remaining time discussing the inverse tan function, which plays a central role later in integral calculus. You might recall from the last video that tan of x heads off towards infinity as x moves towards pi on 2, or 90 degrees, in the first quadrant of the unit circle. We can graph the relationship between x and tan x for these values of x, and it looks like this. And we have similar behaviour in the negative direction if we move in the fourth quadrant from 0 towards negative pi on 2. The lines x equals plus or minus pi on 2 become vertical asymptotes to the curve. Because tan x is sin x on cos x, the periodic behaviours of sine and cosine mean that this picture reproduces itself ad infinitum, both to the right and to the left, with infinitely many vertical asymptotes, which in fact occur at odd multiples of plus or minus pi on 2. Again, the horizontal line test fails spectacularly, so we have to drastically restrict the domain in order to produce the graph of an invertible function. The convention is to restrict the domain to the interval from minus pi on 2 to pi on 2, but not including the endpoints where tan is undefined. So we focus on this very nice piece of the tan curve, which satisfies the horizontal line test. And we can reflect in the line y equals x to invert the function, producing the graph of y equals inverse tan of x, a beautiful shape called a sigmoid curve, sandwiched in between two horizontal asymptotes. Sigmoid curves are important in computer science and the mathematics of neurons used to model behaviour in the brain. Remember, inversion interchanges domain and range, so the domain of inverse tan is the range of tan, which is the entire real number line, and the range of inverse tan is the domain of our fragment of tan, which is the interval from negative pi on 2 to pi on 2, but not including the endpoints. Again, just think of tan as taking angles to numbers, and inverse tan as bringing numbers back to angles. For example, tan of 45 degrees, or pi on 4 radians, is 1. So inverse tan takes 1 back to 45 degrees, or pi on 4 radians. Maybe you conjure up in your mind an image of a 45-degree right-angled triangle with equal opposite and adjacent side lengths. Tan of negative pi on 4 is negative 1, so inverse tan takes minus 1 back to minus pi on 4. Here's an application. The Statue of Liberty is 46 metres tall, standing on a pedestal of the same height. Find the angle theta subtended by the statue if you're viewing it from a distance of 250 metres. Though we haven't been asked to find it, let's denote the angle subtended by the pedestal by another angle called phi. So there's a right-angled triangle with angle phi, with opposite side length 46 metres and adjacent side length 250 metres. So tan of phi is the fraction 46 over 250. So undoing this gives us phi equal to inverse tan of that fraction. There's another right-angled triangle with angle phi plus theta with opposite side length 46 plus 46 equals to 92 metres and adjacent side length again 250 metres. So tan of phi plus theta is the fraction 92 over 250. Undoing this gives us phi plus theta equals inverse tan of that fraction. Taking phi away gives us theta equals this very nice explicit expression involving fractions in inverse tan, and we can evaluate this using a calculator to get approximately 0.17 radians, which is about 9.8 degrees. This solves our original problem. The angle subtended by the statue from 1/4 of a kilometre away is almost 10 degrees. This is in fact the last video for Module 2. Over the course of this module, we've introduced and discussed so many different and contrasting ideas, all glued together by the unifying concept of a function and associated ideas of domain, range, and graph. We've talked about linear functions, whose graphs are lines, and quadratic functions, whose graphs are parabolas, and discussed techniques involving completing the square and the quadratic formula. We talked about polynomial functions, built out of non-negative integer powers of x, which can be evaluated using simple arithmetic. And on the way mentioned fractional powers, which are a neat way of interpreting square roots and other types of roots. We showed how to create new functions by means of composition and inversion, both geometrically by reflecting in the line y equals x and by algebraic manipulation. By changing our point of view with regard to the roles of constants and variables, we moved from power functions to exponential functions and discussed the most important base, Euler's number e. We described logarithmic functions and discussed exponential and logarithmic laws and applied them to exponential growth and decay. Recently, we introduced trigonometry and the sine, cosine, and tangent functions. Just now, we discussed the inverse sine and inverse tangent functions and briefly illustrated how they can be used to interpret numerical information in terms of angles. Please read and digest the notes, and when you're ready, please attempt the exercises. Thank you very much for watching, and I look forward to seeing you again soon.